All right, folks, today we're going to talk about the graph standardization theorem. Essentially, we're just going to put the translations and the scale changes that we've been talking about together today. And we're going to focus on how the equation and the graphs relate to each other so that we can find critical features either from a graph or from an equation when we don't necessarily have both. So you have this practice where you've got some information given to you here, but this same information is on your note card, so you may want to locate that now so you can see kind of where you'll reference moving forward. But what I'm going to have you do is read through the instructions here, and I'm going to have you do just a couple problems first, and then we'll chat about those before we do a couple problems together related to those items. So what I'd like you to do right now is answer questions 1 and 2 after reading these instructions. Pause the video and take care of those for me, please. Okay, so 1, you were taking a look at this graph, and you were using the graph or the equation or both combined to talk about each of these pieces. Now, with most of these, they're pretty straightforward from the graph, meaning domain, range, amplitude. You can find those 3 pieces pretty easily from the graph, but I want to relate them back to the equation as well, because that's really the goal, is tying these 2 together. So from the equation, amplitude is number out front, no problem there. And then the domain is always all real numbers for sine and cosine. The range deals with both these 2 items. From our midline, k, of this 10, we're going to go up 5 and we're going to go down 5 to get our minimum and our maximum of 5 and 15, always included for that. Okay, period on a graph, you find it when you complete an entire lap. So for us, that's easy to see from maximum to maximum, which is from 0 to pi over 2, or a distance of pi over 2. But we also want to talk about the equation for it. On your note card and on the paper up above, you have the formula that tells you take 2 pi, the normal period for sine or cosine, and take it times a. But what is a? So we're going to go back to like purple note card ideas. This 4, remember, means a horizontal compression. And we always use the reciprocal when we talk about what happens on the graph versus what we see in the equation. So this is really 2 pi times 1/4, which gives us pi over 2. Okay, so using your equation as well. And then I gave you a note for h, and hopefully you saw it. If not, go back and take a look at it now. This right here, we are always going to set the parentheses equal to 0 to solve for h, because last year you never saw h and an a value happen at the same time. Okay, it was b on your old note card, okay, but you never saw 2 pieces inside an equation at the same time, and this year we're going to. Scale change is going to affect that, which means we have to let it play a role when we're solving for that translation. Okay, so set that equal and solve gives us our h value of negative pi. So I actually labeled that on the graph here for you, but then I asked, is that the phase shift? Okay, and the phase shift by definition from last class is the smallest shift from the parent function. So in order to answer this question, you have to know what the parent function usually looks like. For cosine, the parent function usually starts at the maximum. So you're going to find the maximum that's closest to the starting point, so closest to that y-axis, and our first maximum is actually on the y-axis, which means no, that is not the phase shift, because this maximum is way over here. It's definitely not the closest. And in fact, we don't need a phase shift at all to get to the parent function if our maximum falls on that y-axis already. We don't have to go left and right. So our phase shift is actually 0 here. Because you don't need a translation to get to this same identical graph. Essentially what we're saying is this is equivalent to 5 cosine 4x plus 10. Nothing extra. There's not needed. If you graph that, it would look identical to this one. Okay? We could also graph it with a pi over 2 as the h value, negative pi over 2 as the h value, and so on. Any of these maximum values, but phase shift by definition is the smallest. Okay? this one, hopefully the conversation about range helped, but a visual sometimes is nice. From that midline, we go up the amplitude and down the amplitude. I do want to point out that the amplitude here is always positive. Remember, this negative just means we have a reflection over the x-axis, which means our sine wave would go down first instead of up from the parent. Okay? Then our period, same thing as last time. We've got a horizontal crunch, so times it by the reciprocal to get pi. Set that thing equal to 0 to get h. But what we're going to do is talk about one other way we can come up with like this range values, and that's going to help us with 3 and 4 that we're going to do together. So to the side here, I want you to write min and max for me. And we've done this a little bit with our Ferris wheel problem, but we're going to talk about it in more detail today. So the old minimum of sine is -1. And what we're going to do is transform that using every operation that would affect it. So when we're thinking about the operations here, since minimum and maximum are a y value, then these two numbers, the -4 and the -5, are going to affect it. When we think order of operations, this -4 is times and this 5 on the end is minus. So when we talk about which one to do first, it has to be the multiplication. So we're timesing by -4. And then we're subtracting 5. Maximum is the same way. We're starting at +1 though. Timesing by -4, subtracting 5. And that tells us 4 minus 5 is -1. And -4 minus 5 is -9. The only weird part about this is you'll notice that min and max are really not in the correct order. That comes from this sign right here being a reflection over the x-axis, which flips these around. Okay, so we can do that algebra, but when we reflect over the x-axis, a minimum goes down and becomes a maximum. And same thing happens with our maximums. They reflect over to be minimums. Okay, so those will trade places. Biggest idea here is making sure we go from lowest to highest when we write it down, which means this thing needs to be -9 first, and then -1. Okay. So now let's talk about how we use this rule to talk about a composite from the equation. So hopefully you remember composite from back in chapter 1. Looks like f of g of x. This opening says following. So we always plugged in this f, or this g function inside of the f function. We're really thinking about this part first. When we go back to here, it's the same idea. We're thinking about order of operations of what would have to go first, and we know we have to multiply first, which basically means we have to make sure when we talk about our scale change and our translation, putting them together, we know our translation happens after our scale change, so we're going to call this t of s of xy. Just like we've seen t of xy for a translation rule, and s of xy for a scale change, we're putting those together as one composite function. Okay, well, as a reminder, for a rule, we had x plus or minus something, and then y plus or minus something, and then for our scale change, it was something x and then something y. And our first part, it was always opposite or switched from what we saw in the equation. What I want you to do is just write down or take a look, it's up to you, at your equation that's on your note card. And we'll pay attention to the letters that they use. Okay, so for trig transformation specifically, they put b out in front, and that's going to be important for what we do. And then 1 over a, and then x minus h plus k. So when we talk about these pieces, the things that go with x are both the translation left and right and the scale change that's horizontal. And dealing with x's inside these parentheses, for us, those two letters are h and a. But both of these things have flipping actions happen. So this says opposite sign, and this says take the reciprocal. And that's what we're going to do when we look at these two numbers that correspond to the positions we see. So here we're starting with our multiplication. So this is 1 over a. We see 4, so we're going to write 1 over 4, the reciprocal. Then x stays, just like in the rule we always had an x show up. And then instead of minus h, we're going to do the opposite. So this says plus pi, we're going to say minus pi. Okay, and the reason this is actually h, because every time we were solving for h before was saying it equal to 0, is because of the extra parentheses. If I take 4 times the quantity x plus pi and set that equal to 0, I can divide this 4 off as if it weren't even there. And that's why that negative pi ends up showing up here. Okay? So if it's factored out like this, which you won't see very often, then you can just switch the sign. Otherwise, you're setting equal to 0 for h every single time, just like we practiced up above. And then last thing is we're going to talk about the y part, and this one's easier because for y, what you see is what you get. There's nothing that switches. So we're starting with the number out in front, which is 3, and then our y, and then the number to the side, minus 10. And that is our rule. And what it looks like formally is the two things that affected this were ax plus h. Remember, we used the reciprocal and we flipped the sign. And then by plus k, we left b and k alone. Okay, we're just focusing on position and less focusing on the letters that represent each, and that's going to make our life a little bit easier. The key, though, is really important is this h part of what we just talked about. If we don't see the double parentheses, that should be what you solve for first. So I want you to write that as a note here. Find h first. And we'll do that by just setting that 3x plus pi equal to 0 and solving. Okay, and now that we know that, we can skip right to the rule. Going in order, ax plus h, flip, flip, by plus k, keep, keep. So we are going to start inside because x is inside here. Okay, we're going to flip what we see. Instead of 3, we write 1/3. And we already solved for h to plop right next to it. We see that the sign switched, and really we just divided that 3 off as well. Then by plus k looks like 2. And there's nothing at the end, so it's just 2y, and that's it. Now, why this is so important and why this is helpful is because we actually have done this already up here. It's useful. Sometimes we get bogged down again in all of the technicalities here, but what we just did right here was the rule for this second part. This right here was by plus k, because we took the b value and the k value and did the things to the old y value that we had, which was 1 and -1. And this applies to any point. So I'm going to give you a couple examples here for this one. We're talking about the sine function. So the sine function starts at 0, 0 and goes up. So the point 0, 0 would be on the original graph. What I can find out using this rule is where the result of this point would go on the new equation. And you just use it by plugging in your x and your y value. This is 0 and this is 0. So this says 1/3 times 0 minus pi over 3 is negative pi over 3 itself. And 2 times 0 is 0. So our ordered pair would go to the right, pi over 3. Now, with what we've done in the past, we could have done that, but this is the first time we've seen a scale change and a translation at the same time. And they will affect each other. So it wasn't the same as just saying it went to the left pi. We had to divide by that 3 as well. So it's powerful for us to figure out what's going on. It also helps us when there's a period change, which there is anytime there's a coefficient here. Okay, we know once we have the first point, it's going to follow this pattern, but it doesn't have to follow the pattern every pi over 2. That's only if the period is 2 pi. So we can also do this for the next point so that we can see really what the pattern is doing. So the next point is pi over 2, 1 on the original graph, and we can plug in those values. So if this is pi over 2, that's 1/3 times 1/2 is 1/6 pi. And then minus pi over 3, a 6 minus a third is negative 1/3. Negative 1/6, excuse me. And then our next one, same concept, we take that y value, plug it in, so that's 1. 2 times 1 is 2. And so our next point would be at negative pi over 6, 2, and then we could see the pattern of every single time we're counting by a pi over 6 distance rather than a pi over 2 distance to be able to graph the rest. It's just one strategy. I'm going to have you now flip over and we're going to switch tracks to talk about tangent. I'm still going to have you try a couple on your own first using these items. Again, you will see these items also on your note card. You're going to answer questions 5 and question 6, and I plan to help you work through the domain because I know that can be a little bit messy. Okay, but pause the video and try the rest of those problems for me. Okay, so here the things that were different are C and D because amplitude doesn't exist for tangent since there is no min or max, and the period starts out at pi. So when we horizontally stretch or compress it's from a smaller starting point. Okay, it starts with pi instead of 2 pi. In this case, it didn't matter because we didn't have any change, but I want to talk about graphically how we can look for the period just as a reminder for tangent, because tangent isn't always obvious to see where the asymptotes are. So it's not necessarily easy to measure from here to here like we do on the parent function when it goes from negative pi over 2 to positive pi over 2. So what I'm going to have you do instead is focus on the starting point of 0. And we normally have a period of pi, so I'm going to mark that off as well. And we're just going to see where the graph intersects those points 0 and pi. And if one complete cycle happens between your markings, then the period is the same. In our case, it is. Okay, that point is in the same position of the curve, which means that is one period. Okay, if that's not happening, sometimes we can see it from the graph, and sometimes it's easier to go with the equation. So with the equation, what you're going to do is take pi times the reciprocal of what you see in front here. Our number is 1, reciprocal is still 1, and we can find it that way as well. So sometimes it's nice to have the equation to use for that. The h value, since there was no number in front, very easy to set that equal to 0 to solve. And then in this case, it was the phase shift, and I didn't put an explanation because I wanted to talk through it here quick. Okay, right now we know two things have happened from what we saw here with our phase shift, or excuse me, our h and our vertical shift to get us to this point, and that came from 0, 0. Basically, if I'm asking you, is this the phase shift, I'm just asking you, is that the closest point to where the parent function normally is? So this would be an option, and it looks pretty close. The other options are along that same line at 4, here or here. But we want the closest to the original, so yes, that is the phase shift. Okay, so now let's talk about domain. When we do domain, we're going to use the thing we just talked about, and that's the rule. We're going to specifically, because this is x, use the ax plus h part of the rule to come up with where the asymptote is when it's not obvious. Okay, so on this one, let's draw in the asymptotes to start with. Okay, so split your lines vertically here. And we're trying to find where these things have gone. We just need to find one of them. So here, we know that we've been shifted over. So normally this is at pi over 2 and it's gone over some. Okay, but there's really two things that could affect it, not just a shift left and right. There's also a scale change, because this is not at 0 to start with. A scale change would in fact change where it's located. Okay, so both of those items we're going to consider when we do this. And all we're going to do is fill in this rule using a little bit of work here. So on top of your equation, I want you to write a equals and h equals. If we see a 1 here, reciprocal is still 1. If I see a pi over 6 here, it's negative pi over 6. And we're going to use those values where we know, or excuse me, with where we know the original tangent asymptote is. So this first one will look like a is 1 times the original parent function has an asymptote at pi over 2, and then plus our h value, so minus pi over 6. We're just saying this was at pi over 2 and we've shifted this pi over 6. We literally subtract them. So 1/2 minus 1/6 is 2/6 or 1/3. Starting out here, we'll say x, as long as x isn't 1/3 pi. That's our first asymptote. But they happen every period after that. And we decided on part D, our period was pi, so we'll say plus pi n, where n is an integer. Okay, so I'm going to have you add one more note here. Okay, this is your ax plus h, and it's specifically a times pi over 2. And then this is your period, and we've talked about that quite a bit. Just like on this one, with sine and cosine, we took our old value and used B and K. Same thing here, we're using A and H. Okay, so with that in mind, okay, let's check these values first. Amplitude none, period, use the reciprocal, H solve for, vertical shift. I want you to try to write the domain using those notes. Pause the video for me, and then we'll walk through it together. Starting out the same way, x can't be the first asymptote. So we're going to go up here. When we see this, we know a is 1/4. When we see this, h, we have to solve for it, and we already did that down here. Negative pi over 2. And we're going to put that together for our domain. So 1/4 times our old asymptote, pi over 2, that's constant. Let's write that parent asymptote. And then minus pi over 2. So this says 1/8 minus 1/2. I want to show you, if you're not really comfortable with fractions, please don't let that be what you hang up on here. You can always just toss this in your calculator by taking 1/4 times our 1/2, the pi, and then minus our pi over 2. So that's just 1/2. And then change it to a fraction. So it's negative 3/8, and we put the pi back on. Okay, so that's one asymptote. And that's not necessarily the first one, but it doesn't matter which one you start with for the domain. We just have to pick one and then say it happens every period after that. In the case of this one, our period is only pi over 4, so it's plus pi over 4n, as long as n is an integer. Now we're going to go the other direction, which is a little bit more straightforward, as long as we know what the equation on our note card says. So we're going to start just by writing that out with our parent function. So that's b cosine, extra parentheses here. And our job is to interpret what they give us to fill in those values to come up with a simplified equation. When I say simplified equation, I just mean don't have double parentheses when you're done. Okay, so we'll get to that when we see it. So here, phase shift goes in for h. Okay, we're assuming they're giving us the smallest value. So here is a minus 3 pi over 2. We always switch what we see. The period is not any of these values directly, but it relates to one of them. Okay, so on your note card it says the period can be found for sine and cosine by taking 2 pi times the absolute value of a. We know our period is 4 pi. So that tells us a is 2. So when we write our equation, this says do the reciprocal of that. So when we write ours outside these parentheses, we're going to put a 1/2. Okay, then I'm going to bring down the second pair and the cosine, and we'll keep working. This says the amplitude is 2, that's the b value. And then vertical shift is -5, just -5 at the end. Okay, we didn't start on the line because we do have to simplify. Okay, we're going to just distribute this 1/2 through and we're all done. So this is 2 cosine, 1/2 x, straight across, 1 times 3 pi is -3 pi. 2 times 2 is 4. And then that -5 at the end. Okay? Really important here, what we're saying is this cosine, so that starts at its maximum, has a phase shift of 3 pi over 2. If we mess up with this equation, we're not going to see that phase shift in the correct spot. Okay, so I'm going to take a second to show you kind of what I mean here. So the graph, or the equation that we came up with was 2 cosine, and then 1/2 x, and then minus 3 pi over 4, and then -5. Now it's going to be a little bit hard to see with this scale, so I'm going to change this to adjust it to count by at least pi, so we can see in reference to what we're going on here. We said the phase shift from our equation was given to us as 3 pi over 2. Not 3 pi over 4, although that's what our equation ended up looking like. And yet, our maximum that was here has shifted over 3 pi over 2. So those extra parentheses are 100% necessary going through here. It takes care of all the other items as well. We can see our period here being from -5 pi to +3 pi is a distance of 8 pi over 2, or 4 pi, okay, which is what we needed. We're seeing the midline at -5 like we needed. We're seeing the amplitude of 2. Okay, but all of these pieces work together using that formatting on your note card. Okay, so I'm going to point out this to you. Number 8 is tangent as a parent function instead of sine and cosine. Okay, but now that I've pointed that out, this one is on you. Okay. We should have had tangent on the inside, then a 1/3 x, and here we're switching the sign and distributing through. So pi over 18 is what you should have gotten, with a +7 on the end. Very last problem here, we're going to talk about an application. Okay, what I'm going to have you do here is think about a couple questions together. This is what I had them do in class. And then we'll talk about finishing it out together. So what I want you to do on your own is think about these 4 numbers and how they relate to the context of the graph, and then how they would relate to this circle talking about the Ferris wheel. Once you decide those 2 things, you'll be able to answer the first and the last question. Okay, so those are the things I want you to try on your own, and if you get stuck, no problem, we'll go over them. Okay, but I want you to try those first, pause the video, and do that for me. Okay, this is our K value, or our midline. This 20 in front is the B value, or the amplitude. This is not quite A, just like we did on the other ones. I'm going to write this to the side. This is the reciprocal of A, so that would be A is 15 over pi. And this -10 is not H, but it's close. It's the opposite of what you see, so H is 10. Okay, those items are going to help us answer questions. It says, how long does it take Darlene to complete 1 revolution? Well, we know that's another name for the period, and we have a formula to talk period. Normally it's 2 pi, but right now we have this stretch compression that's happening here. And so we're going to multiply it by A, that reciprocal, 15 over pi, and those pi's are going to cancel out nicely for us. Oftentimes when we're dealing with word problems, you'll see a pi in the equation which allows our x-axis to get rid of those angular measures and talk about time in seconds or minutes or hours or whatever we're working with. So in our case, this is talking about time in seconds, so that is 30 seconds it takes to make a lap around this circle, which seems pretty fast, but also this is not a very large wheel respective to some of the other ones that we've worked with this semester. Okay, so now that we have that, we're going to skip down this bottom one. It says, what do the 20 and the 10 represent in context? Okay, so this is not on the graph what it means. It means in context to this wheel, what do they mean? So I know the 20 is the B value. I know that's the amplitude. But what does that relate to on the wheel? Okay, so if we think about this, the amplitude is the distance between the maximum and the midline. So here's my maximum, here's my minimum, here's my midline. It represents this distance, which, if you remember from last chapter, is the radius of the circle. So our radius of the wheel is 20, and context tells us feet. Okay, and the 10 we have to think a little bit more about. We know that that is our h value, but we have to talk about context, what it means. So first thing we're going to do is actually attach a label. Because we're inside, we're talking about time, so I know this is 10 seconds. But in order for us to think about answering this question on what it really represents other than 10 seconds, is we need to think about what this graph looks like. Okay, so what I want you to do to the side here is we're going to sketch and add some labels to this graph. Okay, a lot of times in context, we don't have above and below the x-axis. We don't have positive and negatives. We have some minimum value, some maximum, and they're both positive. So for us on this wheel, we know the highest is 45 from the visual. We know the lowest is 5 from a little bit of math, okay, because our midline was our 25, and each distance it was 20. So when we draw this graph, our lowest value is 5, and our highest is 45. And I don't care about anything to the left because I don't have negative time. Okay, but what this means for me, when I say h is 10, I mean that the normal parent function, other than now it's cycling between here and here, it's also going to start later than it normally does. So cosine normally starts at the top, right at the beginning. But for us, we've moved 10 to the right. So somewhere over 10 units, we're starting our cycle. And that's the only scale value I'm going to start with, because now we're just going to know we cycle back and forth between that 45 and 5, back and forth over and over again. And why that's what I'm starting with is because this scale doesn't matter for all the pieces. I just care about the important features. So here, the important feature of this 10 seconds tells me that 10 seconds is where the maximum occurs because of that parent function. So in context, the maximum means the top of the wheel, and we're talking about Darlene. So this says after 10 seconds, Darlene is at the top of the wheel. Okay, and I'm going to do one more thing to kind of connect that to what we did up here. Get rid of some of these extra markings. We found out that it took Darlene 30 seconds to complete a full lap. So right around there, it took 30 seconds. We just found out that this 10 represented the time it took from here to the top of the wheel, here, and this is 10. And I hope that seems reasonable to you, because if I split this here, 10 seconds, 10 seconds, 10 seconds, there's my 30 total seconds to get around the wheel. And now that doesn't have to happen perfectly every single time. This h value is going to be directly related to the parent function. So h is either going to tell you the seconds later that the maximum occurs if we're dealing with cosines, or the amount of time later it occurs where the midline is for sine. Okay, so it's all about those parent functions. Okay. Now, last question, it says, assuming the ride will continue for at least 2 minutes. Okay, so that means we're going multiple laps, 30, 30, 30, 30. Find all times at which Darlene is the closest to the ground. Okay, we can do this 2 ways. We can use our picture here, because we already did the hard work, and we can also use your calculator, and we're going to do both here. This picture is going to go a lot faster just because we've done some of the hard work. If we didn't have this information of the 10 and the max already, that would be something that we would have to find in order to make this work. Okay, so in this case, when we are closest to the ground, that's important for us to realize that that is the minimum. We are finding where Darlene is at the minimum. And we know the minimum height is 5 feet. So graphically, I am finding these values, all of them forever, but we only care about the first 2 minutes worth. Okay? So in order to figure out what this is counting by, because it's not pi over 2, remember, we have a period change, is we're going to use that period to help us. I know that from maximum to maximum, a period occurs. And for us, that's 30 seconds. So this would have to be 40. And then from this visual, we know the distance halfway is 15. So 10 plus 15 is 25. And we can repeat that and keep going, but it's easier once we know one minimum to know that that's going to happen every period or every 30 seconds. So my first one is at 25 seconds. And then I'm going to add 30 seconds again, adding the period, after you find one. Okay, so 30 seconds later is 55 seconds. 30 seconds later is 85 seconds. And remember, we're only going to 2 minutes, so we're stopping when we get a number that's larger than 120. So 30 more seconds is 115, and that'll be the last one that we can find. Okay? The other option is using your graph. For that, we've got to put in the equation. So our equation here was 25 plus 20 cosine, and then pi over 15. And it's really important that you only put in the parentheses they do. So they automatically had parentheses here, but we didn't need to put them. We do have to put in this one. And then we can use x minus 10. And then you can close it twice or once or none, because that's why they put that 25 at the end. It's not going to mess you up if you miss a parenthesis there. Okay, the bad part about using your calculator is you have to pick an appropriate window. Okay, so we don't want this pi looking stuff, because an appropriate window for us is to 2 minutes. So we're going to go 0 to 2 minutes, which is 120 seconds. I'm going to count by 30 since that is our period. And then we already found our min and max was 5 to 45. So I'm going to go 0 to 50. And maybe count by 5s. And then we see our graph looks a lot like ours did. We can put y equals 5 because that's our minimum if we want to trace the intersections. Or we can do second trace the minimum, do a left bound, right bound, left side, enter right side, make a guess. It's going to round all funny, but we know that's really 55. And then again, find one and then add the period to find the others. Okay, I don't care if you use your graph. You just have to find some features. In order to be able to use your graph, we have to know the window. Okay, that's going to be absolutely necessary to be able to answer that question if you're using your calculator. If you have questions on your homework, please, as always, come in and ask.